Okay, back to it. Let's finish off with this example. Sorry, I had to stop right in the middle, but we are back to it. Okay, so the idea here is because of the 26, we're using a t-score instead of a z-score. So we figured out getting the t-score, getting it on the graph, and then we're going to our calculator, and that's where we were going to stop. So when we do a t-CDF, and I'll show you where that is again in a minute, it's going to ask us for our boundaries, as always. So we're going to go 1.569, comma, 10,000, right, going big. But the other thing that we have to do because of the t is we need to follow that with the degree of freedom. So remember that degree of freedom is required. So if we have 26 students, our degree of freedom is 25, right? So we've got to include that in the parentheses. So again, if you're starting fresh, so we're going to go the same place where the normal CDF is. So second distribution, but we're just going to go down a little bit further. So there you see we're at TPDF, but we don't want that one. We want TCDF. So we click enter. Now again, if your calculator gives you the parentheses, you're going to do the way it's on the board. Here, it's giving us prompts. So 1.569, upper would be 10,000. Degree of freedom is 25. Paste. And there you see that it is typed in there just the way I have up on the board. And click enter. And that gives us 0.0646. So 0.0646 using the t-CDF rather than the normal CDF. All right, now remember that that's our p-value. So we'll say that p equals 0.0646. So we went through all of these steps. Now remember, the fourth step is to decide whether we're going to keep or reject the null. So we're going to compare our p-value to the alpha that we were allowed. So we're allowed a 5% chance of screwing this problem up, but is our p-value lower than that, or is it higher than that? Okay, it's higher, isn't it? So we're going to say our p is actually greater than our alpha, which means that we have to keep the null. Now, keeping the null only means that we're erring on the side of caution. It only means that we're saying there wasn't enough evidence to support our claim. Does that mean we're wrong? No, it doesn't mean we're wrong. It is very possible that my stat students do score better, but in this situation, we didn't have enough proof. So that's the way we write our sentence. So for our fifth step, we say, there is not enough evidence to support the claim. We don't even need to say what the claim is, and it's better that you don't. You just say there's not enough evidence to support the claim. Now, that means to the people that are studying this, it either means they need to go back to the drawing board, okay, maybe they need to try again, maybe get a bigger class, take a sample from 2 classes maybe and see what their sample size looks like there. But all we're saying is there wasn't enough evidence to support the claim. Okay. So again, it gives us, we're just backing up and saying, we don't know, try again if you want. All right, so there is another one. Let's see what I got next. Ooh, we're already way down here. Sounds good. Okay, so let me write the next one up here. Dogs sleep on average 17.2 hours per day. I think my dogs sleep a different amount. I watch my 5 dogs and find they sleep the mean 17.9 hours with a standard deviation of 1.75. Am I correct at alpha equals 0.10? Okay, so again, totally made up example here. I was just noticing that my dogs are couch potatoes, but then it occurs to me, like right now I'm in the barn and they are here hunting, I think, mice with me. So they're not sleeping now. So dogs sleep on average 17.2 hours per day in my world. I think my dogs sleep a different amount. I watch my 5 dogs. Now, as I'm only looking at a sample size of my 5 dogs, what is that telling us? Is that telling us a Z-score or a T-score? So hopefully that's screaming at you that this is a T-score. So just some things to note. All right, then we are allowed an alpha of 0.10 or a 10% chance of screwing this up. So there's a 10% chance allowed that we'll make that type 1 error. Possibly they're allowing us a 10% chance because maybe the study isn't super serious. So it's not like life or death or anything. So 10% chance of screwing it up. So as always though, we'll start with our hypotheses. HO and HA, so the null hypothesis. Now notice, I want you to notice that they're using the word average here in the problem, and I want you to get used to that because when people in the real world talk, they tend to use the word average, but they mean the mean. So you gotta get kind of used to the fact that people are gonna use those words interchangeably. So we're being told that our mean is equal to 17.2. Now, what do I think? I think that the mean is, and I wasn't very specific, I just said different. So remember that different translates to a not equal to 17.2. So mu is equal to 17.2 and mu is not equal to 17.2. Now, this actually causes us an issue. This means we're looking at a two-tail test, which is going to come into play later on in the problem, right? Okay, but from there, we need to go to our next step, which is to find our test statistic. And keep in mind that this one is going to be a T-score. We already decided that. Max, go in and ask Grandma. Sorry about that, guys. Test statistic, so we'll say T is equal to our mean, which was 17.9, minus the original, which is 17.2, all over the standard deviation of 1.75, divided by the square root of 5, right? Teeny square root there. Okie dokie, so once again, we will stick that into the old calculator, 17.9 minus 2, enter, divided by, helps if I hit divided by, screwed up, quick, divided by, parenthesis, 1.75 divided by the square root of 5. Yeah, talk about pain in the butt. Okay, so I got 0.894 here. And remember that this is a t-score. I know it looks like an area right off the bat, but it's a t-score. So we immediately want to go ahead and get that on a graph so that we visualize this correctly. So if we put this guy on the graph, a t-score of 0.894, maybe is about there. This is 0. Okay. Now, the deal is, though, is that this is a two-tail test. So while we're shading this way, we also have to keep in mind the two-tailness, that we went both a greater than or a less than. And really all that means to us is that instead of a p-value, we need a 2 p-value. But we'll get to that in a second, okay? So we do need to find our p-value here. And for this one, we are going to use the t, not the z, right? So we're going to go t, CDF. We're going to start with a boundary of 0.894, comma, 10,000. And then remember, we need our degree of freedom, which in our case is going to be 4. Okay. So go find that, stick that in the old calculator, and see what pops out. I got 0.2109. Does that sound good to everybody, hopefully? Okay. So our p-value is 0.2109. But what did we just say? Because of the two-tail, we need 2p. So we don't want this guy, we want 2p, which is going to be, if we multiply that by 2, will give us 4218. Okay, good. So the 2p, so that probability that we make a type 1 error in this case, is 42%. So remember, we were only allowed 10%. So if you come back with a probability, the probability I screwed up is 42%. Does that sound good to you? If you come back with that number, 0.4218, did you do anything well in this problem? No, okay? This was bad problem, it didn't work. Sample size is too small, numbers didn't work. This is definitely an issue where when we look at this, 2p is super greater than our alpha, okay? So far greater than we don't even want to talk about it. So there is definitely not enough evidence. So we're going to keep the null and say there is not enough evidence to support the claim. So a couple things that you're noticing that you have to look at when you read these problems is you have to look for your sample size, and then you also have to be checking on those, checking on those hypotheses to decide whether you have a one-tail or a two-tail test going on. Okay, so let's go ahead and do one more. I think I have one more. I do. All right, so the average Burmese python is 14.8 feet long with a standard deviation of 2.96 feet.
Max.
I think pythons, guys, put it down. and go away. I'm working in here. I think pythons living in Burma, which is now Myanmar, aren't as long. Trekking through Burma hold on, you guys. Okay, I'm almost done. I need you guys to go do something else. Sorry, got kids running around. Okay, so trekking through Burma, I sample 31 pythons and find their mean length is 14.1 feet. Test the claim at alpha equals 0.10. All right, now I don't know about you, but whether or not you're looking at a 14.8 foot Burmese python or a 14.1 foot Burmese python, that's large, right? So the Burmese python is the largest snake in the world, and just so that you get an understanding of how large a Burmese python is, the next time you're driving down the road, look at a telephone pole. Okay, think about how wide around a telephone pole is and how tall a telephone pole is. A Burmese python at its largest is as large as a telephone pole. Can you imagine a telephone pole slithering down the road? Yeah. Okay, anyway. So again, we're using the word average, but that in the real world translates to mean, okay? So we're looking at a mean problem. There's the word mean again. Again, I'm trying to give you the information in lots of different orders and organizations just so that you can see different ways that will come to you. But always first is our null hypothesis and our alternate. So we're studying the mean, and remember our null is just that blanket statement that says that the average Burmese python is 14.8. So mean is equal to 14.8. Then what do I think about the Burmese pythons that actually do live in Burma? I think they aren't as long, which means that we're going to go with a less than 14.8. Okie dokie. So we need our test statistic. But in the last two examples, our test statistic was a t-score. Tell me about this one. Our test statistic this time is going to be a z-score, isn't it? We got over 30, so we're going to use a z-score instead. So we're back to z's, but see how you have to go back and forth from problem to problem. So we'll say z equals, and then we'll start with our number, 14.1, minus the 14.8, all over 2.96 over the square root of 31. So fiddle that away in your calculator, and let's all hope we get negative 1.32. Okay, that's what I got in my calculator. Okay, so then again, it's always nice to see it on a little graph just to kind of help you see what's going on. So if zero's in the middle, oops, helps from on the right side, negative 1.32 over here. And remember, by looking at this or reading the problem or looking at this, we want the mean to be less than. So we're over here to the left side and we want to make that left tail. And again, that tail is our p-value. But on this one, do we need a 2 p-value? We don't need 2p, we just need a regular p-value. It's a one-tail test, so we're good to go on that. All right, so when we go to find our p-value and we go back to our calculator, now you've just gotten the habit of doing 2 of the t-scores, but this was a z-score, right? So we're going back to our normal CDF. And the normal CDF, we'll put in our boundaries, negative 10,000 to negative 1.32. We don't need anything else, just that. Okay. Stick that in the old calculator. Take a minute to do that. And hopefully you end up with 0.0934. So remember, that's our P, 0.0934. So that p-value is just a teeny bit less than what we were allowed. We were allowed 10%, a 0.10, and we came back with a 0.09. So we are less than our alpha, aren't we? Just barely, but we made it. So we get to reject the null. So that means we can throw out the null hypothesis, and the only thing floating around anymore is the alternate. So by sticking with the null hypothesis until we've shown enough evidence, we can now say that there is enough evidence. Not that we proved it, all we know is that there's enough evidence to say. Okay, so there is enough evidence to support the claim that Burmese pythons are not as long as average. And then remember, we're supposed to say at alpha equal 0.10. All right, so remember that it all comes down to the end that there either is or there isn't. There is enough evidence to support our claim, or there's not enough evidence to support the claim. So the answer is never yes, we're correct, or no, we're wrong. Okay, we're always hedging our bets because statistics is never 100%. Okay, so when you go to do practice problems, remember, you're looking for sample size. You're looking for the word mean. You're looking for the greater than, less than, not equal to. That's what you have to read into each question before you actually get going on the whole thing. Once you've figured out all that information, then the steps are always the same. Okay, so you can do that. All right, I'll see you next time for more.